So my name is Takuzo Chikwanda. Today I'm going to be talking about 3D object classification using point clouds. As we all know, 3D objects have many forms of representations. They can either be represented, 3D objects can be represented as mesh, and can be represented by volumetric, by projected view, and also by point clouds. So they can be represented as wireframes, and they can be representative as objects, and they can be represented as points, like the point cloud. So unlike 2D images, which are just X and Y, 3D has more representations. So point clouds are basically a set of are basically an array, or maybe a set, yeah, a set of points, which each point is either x, y, z, and other things like RGB, intensity, and so forth. So the main idea behind this whole project is to be able to detect an object in 3D space and be able to classify it as an aeroplane, as a car, or etc. So the main problems that are still there. That's the reason why automated driving is not yet 100% safe. It's because of these three factors. Point clouds, they are permutation invariant, meaning to say, if you take a set of points and you order them in a certain way, and you do n permutations of those points, you still get the same object. After switching the points, you still get the same object. The order of the points in the array doesn't really matter. What matters is the xy value. So whatever that xy value wherever place you put that xy value, you are still going to get the same object. They are also transformation invariant, meaning to say, after you skew them, or you rotate them, or you shrink them, you are still going to get the same object. So it's a problem. And then there's the issue of point interaction, that points, they formulate something. They are not independent, but in point clouds, it's sort of like each point is sort of like independent. But in actual fact, 2 points, they form a surface, and they form an object. When you cluster them together, they form something that is meaningful, rather. So I want you maybe to just visualize this whole idea of point clouds. What are they? Maybe you can get some ideas. So this is the point cloud I've been talking about. This is a table. It is so when you rotate it, it's still the same object. When you zoom out, it's still the same object. When you zoom in, it's still the same object. So that's the data set. So there's an architecture that worked on this point cloud. It is called the point net architecture. It takes in n by 3 points, and then it transforms the n by 3 point, and then it multiplies it by the 3 by 3 matrix, and then it gets the n by 3. Then it passes it through the multi-layer perceptron and gets the n by 64. Then from the n by 64, it does a transform until it gets the 40 scores for the 40 objects. So the one with the highest score now becomes the object. So they use softmax for that, just for simplicity's sake, just to put it maybe in a more relatable way, which are more like probabilities, but they are not really probabilities. So this is the TNet that is in this point architecture. There's the part that says TNet. So this TNet architecture works like this one. So it produces a 3 by 3 matrix, which is then multiplied by the n by 3 to get a new feature matrix. So what I did is I took those n by 3 points, and then I found 2048 furthest points, took for 2048 furthest points from that network. Uh, and each point is 3 dimensions, X, Y, and Z. And I discarded the rest. There's stuff like RGB and all those. I discarded the rest, just took the X, Y, Z, and then passed it through the convolutional layers, which just transforms the whole matrix and doing all those convolutions, and used a sigmoid for activations. Uh, and then after that, get 2048 by 2048, then do a max pooling from those and then got 2048. Then from those 2048, um, then put on the fully connected layers, which then multiple fully connected layers, which then to be able to come out with 40 scores for the 40 classes. So more layers with sigmoid, they seem to overfit somehow. I tried to shift the sigmoid function to make it work to reduce the vanishing gradient effect, but still they seem to overfit because it's still good on the training data. It can still classify very well on the training data, but on the test data that it has not seen, it's finding difficulties. Then I reduced the number of layers and then put less layers with sigmoid, and then achieved a high accuracy. I really don't know the science part to that improvement, but I'm yet to really investigate on that one. So the point net now is fewer layers. It uses the ReLU function. They really did some good work. I so they got an accuracy of 90%, which is a bit higher than what I was able to get. Now, in conclusion, after changing and making some changes and adding more layers, and they're still changing the activation functions, still the accuracy did not even improve. So it's still a challenge. And then for future work, I believe that these image classification models can also be used for 3D point clouds. I'm not yet. So yeah. So this Redsmith 50 and the yellow VGG16, they can still be used for that. So these are my references. Thank you very much. Time for questions and contributions.